Grand. People will probably still trickle in as we do this, but welcome, welcome. This is probably going to be the most complex topic we're going to cover this year. Um, quick poll for the people who are here. How many of you have used one of these systems before? Like a diffusion, make an image type of thing? Show of hands. Yeah. Sorta in the back there. Yes, here. Yes, there. Great. Okay. So this isn't something that you guys probably have never heard of, but in case you haven't, we'll quickly cover it. Image diffusion, in this case, is the process of generating images that have never been seen before. It's generating images that, one sec, is generating images from noise. So images that have never been seen before or that do not exist get made from nothing. And this is in theory a very, very cool process. And we'll cover today in a very, very high level. We're not going to get into anything very complicated, how this works and why it's useful. But this is generally the process. So you start out with a bunch of noise, and through magic, basically, you're able to make an image that does not exist or has not been seen before. And the really cool bit is that because of how the images are represented in the way the model considers them, you're able to combine features from different images into something that's unique. So if you wanted to make a corgi wearing a Santa hat, even if the set of data that you would have trained on is very, very slim, you'd be able to make an image with that very easily, simply because you're able to combine these features in this way. And we'll cover about in a little bit of detail how this works. But does the concept of what diffusion in this way make sense to everyone? Thumbs up? Feeling good? Cool. Okay. So there's three key questions that we're going to be answering today with a bit of background before we get into them. The first one being, what is a latent space? And a few of you have probably heard of this, but this is a very, very important concept to understanding how modern diffusion systems work. The first version of this actually didn't have it. I think the first diffusion model was made in like 2019. It was used for like texture in painting. It was very, very simple. And it didn't have a latent space, but we'll cover why a latent space is very important, why it's very useful. Second thing we want to do is cover how the learning process works, because I say that it does it magically, but there is some element of machine learning there, a very big one, in fact. And it's important we cover that. And then the third thing that I think is very important is just some of the ethical associations that are to do with this technology, because there's a lot of those, and it's trite. If you guys have been seeing any discourse around AI generated art, you'll understand. Perfect. Okay. So let's cover some important background, and feel free to raise your hand, stop me at any time, because this is a little heady, but this should give you a decent understanding of what we're covering and overall how the model works. So we'll get going. So as a quick exercise, let's follow the highest probability, right? So as a quick question, which one's bigger, 0.8 or 0.2? 0.8, very beautiful, amazing. Couldn't see that coming. Okay, so we're at 0.8 now. We can ignore everything that's in this bottom. It does not matter to us. We do not care about it whatsoever. Which one's bigger, 1% or 10%? 10%, right. Okay, so what's the problem with this? Inherently, right? We have this value here. This is just literally the product of probabilities that led us to this conclusion. This is, as we assume, the most probable continuation based off of the prior step. We'll get into what this is called with a bit more concrete definitions in a second, but what's the problem with this? We reach this conclusion, we followed a very high probability on each step of the way. What's the issue? What are we not seeing? Yeah, exactly. So in this case, if we just took the path of lower probability over here, we would have had two significantly better options than what we actually ended up with. On its face, this is a pretty big problem. It means that we're not going to see the outcome that is most probable at the end of the day. But if you extrapolate this out to say 1,000 terms, the odds are that the discrepancy is going to be very small. And this is called a Markov chain or a Markov process. Basically, the idea is that the current state only depends on the previous state. So there's a few advantages to this. Basically, the main one is that you don't need to know anything that came before. And this was very quickly. It also was able to be solved quickly. So in this case, it took us no time at all to say, oh, we know what the product of the probability is, because we don't need that. We can just look at what the highest probability is and continue down that path. And that means that we're able to do this very, very quickly. But the problem is we have memorylessness. So if we go back a slide, quick, we can see this same issue here. Had we been able to think in advance and say, damn, we have 0.2 here, and then here we have much higher probabilities, we could have probably backstepped and done something that was a bit more valuable. we would have been able to have a much better outcome. But in this case, oops, I went back again, zip it down. In this case, we ended up not being able to do that. We have no memory. We don't know what came before. We only know what's immediately into the future. So this is the process. This is the concept of a Markov chain, and also is the basis for how noise gets added for training a diffusion model. So diffusion, if you guys are familiar with the process in physics or chemistry, is the idea that stuff goes from an area of high concentration to low concentration, diffuses out. So if you have a gas that you release from a capsule, it's going to spread out throughout a room. So that's basically the same concept, but instead of diffusing the from point out into a space, what we're doing is we're adding noise into our data. So for example, if you start with an image of a cat, like we showed at the start there, what you're going to do is add progressive amounts of noise, and the model is going to learn where that noise is. And so you can do this in a probabilistic process. So the noise we add is a lot of time called Gaussian noise. Does everyone know what that means real quick before I continue? Gaussian noise. So Gaussian noise is just, if you're familiar with the normal distribution in statistics, that is the type of Gaussian distribution. It's just a way to represent the likelihood of a probability in a bell curve. And there's a bunch of features that you can define for that, but generally speaking, that's what matters here. And so what we do is we apply this noise pattern over our image over some map steps, right? Through this Markov process in a way that is most probabilistic. And basically, because this adding and removal of noise is an iterative process that we can define with a set function that is Gaussian noise. There is a differentiable element to this, and we know what gets added like in a set way because of just literally probabilistically added noise. We can assume that basically the next most likely step will occur, and we can get rid of this iterative process and stop anywhere in one step. So what this means is we can go from a completely denoised image over here to complete noise in one step, or from completely denoised to an intermittent noise in one step. And this is very useful for training, right? Because the way the model is going to learn, and we'll cover this in a bit more detail soon, is we want it to learn the pattern of the noise. So we need it to be able to generate images with intermittent steps of noise. So say we have some image that we're using as training data. We're going to apply 500 steps of noise and ask the model to replicate it. And the way that it's going to learn is by getting very, very close to that over time. And the thinking is basically, if you're able to replicate any step of the noise, in theory, you should also be able to go from complete noise to having a new image, right? Does this make sense for everyone? This is basically the guiding principle for why this works. We feeling good so far? Thumbs up, sideways down? This is complicated stuff, but I'm glad everyone's following it. Perfect. So the next thing we need to talk about is the concept of a latent space. So does anyone know what this means? Have you heard of this? Does it ring any bells for anyone? Perfect. All right, we'll cover this. This is part of the slide. Basically, I want you to quickly imagine a collection of images, yes? So let's say every animal with 4 legs. So the kittens, dogs of any breed, horses, all of them have features in common. Yes, the 4 legs, 4-leggedness. And they're going to be in a collection of space, like some higher dimension space. You could plot this out. You don't know what it looks like. It doesn't particularly matter. But for this case, we can imagine that this is the big circle that contains every single dog and every single cat and every single horse, etc., that has 4 legs. That's the uniting feature. And so in theory, we can define this latent space by giving it a bunch of additional data points. So like say we have a new picture of a cat, it'll go here. And we have a new picture of a dog, it'll go over here. And all of them should in theory lie in the latent space. And so by getting a larger and larger collection of images, we're able to let the model figure out where that space is. And so basically what we're doing, if we go to the next slide, is we define from the image space here some sort of latent representation. So we're going to pass all of our image data through what's called an encoder decoder network. So more or less, you have a color image, so 3 channels, red, green, and blue, and we're going to transform that through a learned process. A very popular way, we'll talk about this in a little bit, or mention it again, is called CLIP, if you want to look this up. It's a thing released by OpenAI, I think in 2021, where basically they condition on text and images, and it allows you to spit out a mathematical representation of what that should look like in a latent space. So latent in this case, remind me if I'm wrong, I'm pretty sure latent just means hidden. So you don't know the shape of the space, you don't know the size, but you know that it's there and you know how to get there. You pass what you start with through this encoder into this output here. And all of that conveniently through this transformation in this now latent vector space, because we're working with numbers, all of them are vectors, has all these features. So if we go back, we can imagine, I went back 2 slides. We can imagine that this here, this is after some sort of transformation. All of these, through whatever transformation, found out, all of these have 4 legs, we're going to represent it in this latent space. What that means for us, basically, is if we were to pass all those images through an encoder, the output of them would lie in this same space. And that's basically the process of transforming the data into something the model can use. We feeling good? Awesome. Awesome. And the neat thing, right? The diffusion occurs in this latent space. All of it. Every single thing. So what's really, really cool is that because the latent space is actually differently sized and actually smaller a lot of the time than the input space, you're able to do the operations faster. And the extra cool bit is that after you do the denoising process, you're able to then decode it through basically a reverse process that's also learned into a new image. And that's really magical. It allows you to do things very, very quickly and generate a new image from basically math that's incomprehensible to people in a very, very fast amount of time. Like you can generate an image with stable diffusion that hasn't existed before with sufficient computational power in under a minute. It's like 4K in resolution, depending on like what hardware you're using. But it's a generally very efficient process, and the bigger the network, the longer it takes, of course. But generally, this is the process and why it's actually doable. Speaking of the learning process, are we feeling good so far? Concept of a latent space, why it works, why we use it. Very good. Very good. Okay. The learning process, yes? Everything comes down to noise. All of it. So because we can choose the amount of noise to add to our different image, I know I've mentioned this already. We can do this in an iterative process by adding this Gaussian noise. The model learns how to denoise the original image. And we're able to get an entirely new image solely from this process. So combining these two things of the Markov process of adding the noise, which we're able to collapse into a single step, and the latent space where we're able to extract features from just a collection of data that's been transformed, we're able to take this and generate something. Now you might be asking yourself, that doesn't make sense. It doesn't tell us how we're informing the model of what we want. And you're right, I haven't mentioned this yet. But basically, on its face, I don't have this anywhere in the slides. The idea is, say you want a condition on text. The same encoder can be used to transform the text as well as the images in order to get the features out that you want. So more or less, right? And I could be slightly wrong about this. It's been a while since I've looked at the paper. What you want to do is take let's say you're conditioning to find like a dragon and a cowboy hat, which is not a set of image, is not an image that you're probably going to find anywhere. But you say that, you give it to the model, it's going to transform it, and from that collection of images in that space, you're going to retrieve out something new from that through this process. And basically, the way that it does it is more or less just checking how similar that is. It's a sum of vectors. So I could draw it on the board later, but more or less, let's say the feature for dragon is like in n-dimensional space on dimension 3 is like +3. So you're gonna have a vector there, and then the hat is gonna be like -5 on dimension 17 or something. You're gonna add those together, and you should find a collection in that space that will generate that image. This is an oversimplification, and I know I'm kind of speaking in general without a diagram here, and that's kind of difficult, and I'm sorry. But this is in general the process. So through this learning how to iteratively remove noise, you're able to get a new image. And if you don't want a condition, you don't even need to do that. So if, for example, you just want an image that looks like your training data, you don't need to give it a condition. So a very good example for this is landscapes. Say you have just a collection of landscapes and you want to generate a bunch of windblown cliffs, yes? What you're able to then do is just give the model a whole bunch of cliffs to train on. It learns what those cliffs look like, and then you just ask it to generate an image, and it'll sample from that latent space and give you something that hasn't existed before. Not from the training data, not from any other model that's generated this. And That's more or less the process. And so by conditioning on the noise, you're able to learn this, learn where the thing learns, and continue. I don't have any images of the learning process, but it's basically it. Okay, great. How are we feeling? Good? Yes? Excellent. Okay. So how many of you have been on the internet in the past, I don't know, year? I'm gonna guess everyone. I don't know why I asked, but like generally speaking, you guys have seen the kerfuffle associated with AI art, right? What do we think about that? Like, just this is not like a right answer type of thing. What do we think? Is there some amount of like copyright infringement for training these models? Like at the end of the day, it's generating something new that's very similar to what already exists. So there's a good argument. Similarly, for any generative model, actually, there's an ongoing lawsuit right now between like the New York Times and a bunch of other people against OpenAI because they found that they could get ChatGPT to regurgitate copyrighted New York Times articles, or very, very close to it. And that violates their copyright, obviously. But what do we think? How concerned should we be about this? What can we do to prevent like data theft for this type of image generation? How do we add protections? What do we think? This doesn't need to be serious, but just like anything that comes to it. Should we be concerned? How want me to protect against this? I know, yeah, that's super unfair of me. No clue. That's fair. I mean, like, just to add to this, there is a very troubling trend of people specifically scraping an artist's work from the internet that they put out there to show off their work, find people to like hire them to commission art, and then just like emulating what they've made in about 20 minutes, instead of like years of practice. And it's troubling. Like as someone who enjoys seeing people create and what they can make, it's a little troubling to see like someone just be able to take all your work and spit something out that's very simple. However, this isn't all for lost. So like I mentioned, these are from last year, actually. I found these headlines. I almost scraped, but I found these headlines on Google from a year ago. Obviously, art isn't dead at this point, like the bottom one contends or like anything else. But yes, someone entered a stable diffusion thing into an art contest and won. Yeah, people are generating stuff with DALL-E 2. Actually, DALL-E 3 is available now. If you guys want to try it on Microsoft Edge, you just have to go to like their Copilot tool or whatever. And it's problematic. Like anyone can generate art that is in theory competitive or looks like anyone else's art. And it's a problem. But people are smart. Computer scientists are very smart people. And they've made some cool stuff. So this is a tool from UChicago. At this point, it's in version 2.0, actually. This is a slide from last year that I've only changed a little. That basically is a tool that protects artists from styling. So one of the main things that these models can do is given like, they train the models, right? So for example, if you guys have heard of Stable Diffusion, those models are pre-trained and then released. So you can prompt it and it'll spit out an image for you. But if you want it to do something very specific, you can give it a set of your own images, let it fine tune on that, and then ask it to spit out something else. And it will. It'll spit out something that basically looks like that same style. Which, you know, might be very useful for some cases, but also is a violation of artists' copyright, but it's complicated, right? You can't exactly copyright a style, you can't do a lot of this stuff. But what this tool does basically is make it harder to mimic someone's style by adding noise. Now I know what you're thinking. That doesn't make a lot of sense. How can you just add some noise to a thing and make it ignore it? But it's cooler than that, because what they do is they use the same process that scrapes it to generate what are called style masks, which basically just represent style of a different artist. So let's say you're doing something in a hyper modern style, right? What you could do is put a Baroque style on your image. So just like patterns that are associated with Baroque imagery, Baroque art in a way that's imperceptible to the average person, that's imperceptible noise. What will happen is if someone scrapes those images and tries to duplicate them, it poisons the data set. They will not be able to generate art in the same style. And it's really, really cool. So if you look down here, this is an example. So like here's an original work, and I'm sorry the projector has terrible resolution, but this is an original work by the artist that hasn't been touched. So like the artwork style gets mimicked very, very exactly, and wow, it sucks. And so then here you can see by adding additional noise, it makes less and less sense and begins to mimic Van Gogh. And then in the bottom, I don't even know what that style is. Maybe it's Monet. But any art that you want, so long as the style is distinct, will have good results. I haven't had a chance to look at the 2.0 work yet.
Brad for who's the first version?
Really?
Yeah, it was very easy to buy. When it worked, it's easy to buy less than.
Oh. Interesting.
Take it what you will.
Hmm.
It's also very easy to just undo.
Yeah, because it is just a pattern of noise. But you have to know what it is. It's encoded in that. But yeah, it's hard to protect against this stuff. And version 2.0, I imagine, does stuff better. I haven't had a chance to look. My internet has been terrible today. But yeah, these are just some of like the general protections that people have been working on and continually improving. It's a race. Like it's the same thing as in my opinion, as cybersecurity. If you put up some sort of firewall, someone is going to be able to break it. If you put up some sort of network protocol, someone's going to be able to break it after some time. It's a back and forth.
Putting it's not a perfect solution. It definitely has some effect. People will just walk into your property, but it's not possible.
Yeah, yeah. It's a deterrence, basically. It's a cool project. I would look it up if you are someone who produces art. Look into it. There's no harm putting it on. It just adds a bit of noise. It's pretty imperceptible at lower levels. It's neat. Just tell people about it. I think it's a very cool project. And it seems to work well, at least from the metrics I've seen. I haven't seen one coincide. Yeah. Cool. So stable diffusion. We feeling good so far? Topics all good, making sense in our brain. I know this is a bit of a hard left turn in a stable diffusion after talking about how, man, people are stealing style and you can do it so easily and blah, blah, blah. But no, this is just generally the process, yes? So hypothetically, right? Stable diffusion by Stability AI is an open source diffusion. They train it, they publish it, and then on your own machine or on a server, you can generate a bunch of images, things that do not exist, and make whatever you want, put it wherever you want. It's very useful for visualization. It's useful for doing whatever. There's a bunch of different checkpoints that people have made for specifically tuned things, specific negative prompting that we're not even going to cover because that's way too complicated for this. But it's cool and it's publicly available and it's free. So here's generally the process of what a prompt would do to generate this sort of, right? So we start out with like anything. You could pick anything. In our case, we just were like, purple monkey on a horse with a spear gun. That came from my brain. Lots of craziness up here. Yeah, so let's say we want a purple monkey on a horse with a spear gun. And shockingly, I don't think you could find an image of this on the internet that exists, because why would you have that? That makes no sense. And from there, what you do is you pass this into the encoder. I know I mentioned this already, yes, but basically, because English doesn't mean anything to a computer, it means words to you and I, but same way that like actual code doesn't mean anything. It needs to get translated first into assembly, then into like machine code. You need to take steps to make it comprehensible. You need to make it a way that the computer can comprehend it in this case. And because English is super far removed, we need to transform it. We pass it through an encoder. We get an embedding. So an example that I mentioned earlier is clip. There's another one called glove. There's a number of these that basically do the same thing for slightly different purposes and slightly different lengths of time to work. That basically encode English language into a vector, into a bunch of numbers that are comprehensible by a machine. And from there, we feed it into our prompt. So we sample from noise. So we take from basically just random noise, initialized to a bunch of random colors, and then let the neural network denoise it. So we just give it stuff. We give it the prompt, we pull the features that we want and let it create the new image. From there. I know it's not very detailed, but unless you guys really want me to get into like the exact neural network, which I'd rather we don't because it will be very difficult for all of us. This is the overview of the process. And through this, you're able to create basically anything that you want. Any singular image, there's projects that actually make video from this. I think OpenAI's is called Sora. I think there's a build of Stable Diffusion that does this as well. It's like Stable Diffusion video. That one's weird. It made like it was like Will Smith eating spaghetti or something. I remember seeing it just looked weird and noisy and horrifying. Yeah, this is generally the process of learning. And so from this, you can create stuff. And I will say this is a very, very loose overview of the topic. This is not nearly enough time, the amount of time that we have, an hour, to go into this to a level that makes sense to everyone. I would need to cover basics of autoencoders, of like how clip works, of how like the neural network that this is based off, it's called a U-networks. There's a bunch of linear algebra. You need to know how a transformer works because this is actually based off of the transformer architecture. So like think ChatGPT type of thing. There's a lot of basis to get a system that works like this. And fundamentally, it is very, very difficult to cover that. But this is kind of an overview of the process. So if you're interested in this, to learn more about how you would program this, how it looks in code, you have two options. The first one, this little notebook here, this is very complicated. We provided this notebook last year. It's an example from Hugging Face, I think, where basically it is a very complex and well-written example of a diffusion model. I think it's to generate numbers, maybe. It's been a while since I've looked. Oh no, sorry, it's to generate shirts. It's very complicated. It's a long notebook. It has a lot of math, and it goes very, very into depth, much more than I could in the amount of time that we have, into the content of how this looks. And then the other one here is much simpler. This is a very simple, unconditional diffusion model. It generates just a bunch of cars. The other one is too, but the top one goes into significantly more detail and depth to do the generation. But yeah, if you guys want to check this out, both links are here. We can write them on the board. And then yeah, if you guys would be so kind, I know we have a lot of time still, so I can answer any questions that you guys want about the process, or we can go through the code. But this is difficult stuff. Please fill out the feedback form. This is the hardest meeting that we do every year. Did it last year as well, and I think this one went better, all things considered. We didn't go nearly into as much neural networking stuff. Yeah, let us know how it went. Give us feedback if you can. We'll use it to improve this exact slide deck for next year, hopefully making it even more accurate and less confusing. Let us know. Check out the code. We'll spend some more time here, definitely on the code for a little if you guys want. But that more or less is it for the content. So I think, yeah, I think we can pause the recording at the very least and spend a bit of time looking over the code.